come to speak this morning about plant life extension and recent developments in EDF's nuclear fleet. This is the EDF fleet, 58 reactors in operation, 1 EPR reactor in construction. The fleet is deployed over 19 sites. This is well known. On slide 3, the status of the French nuclear units for extended operation. We have on our 900 megawatt series, we have 18 units which have completed extension for between 30 years to 40 years. And of these 900 megawatt units, 5 units have been formally authorized for 10 years, beyond 30 years, so this is the Desagnan visit, 30 to 40 years. And there are special requirements to be performed. This is was by our regulator, and the famous example is the basement thickening at our Fessenheim units. The slide also points out that in the US, 73 units out of 100 reactors in operations have been granted a license extension up to 60 years. Now, we have spoken this morning about a non-replaceable mechanical component, the reactor vessel. So I give on this view graph the status for the lifetime up to 40 years. For 900 megawatt units, this vessel safety case has been accepted by the regulator in June 2010 for all units, but there is a provision for in-service inspections and control during the third 10 years outage. For the 18 900 megawatt units which have performed modifications, and this includes Tricastin 1, there is a special provision for inspection every 5 years. So yes, this is a special reactor vessel. There is a special provision, but we can use it until 40 years of lifetime. For the 1300 megawatt units, which are a bit younger, we have sent a safety file to the regulator in March 2013, and the regulator's position is expected in 2015 for beyond 30 years. I point out also some favorable features for French reactor vessels. The steels at the design have been chosen for the capability against irradiation-induced embrittlement, which has been spoken about this morning. We perform extensive fabrication controls, in-service inspections, and controls every 10 years since the very beginning. Also, a technical indicator, what is called the transition temperature for ductile to fragile. And for the 900 megawatt units at 40 years, this transition temperature, which is used as an indicator, is low, 60 to 90 degrees C. When we take a look at American units at the same age, the transition temperature is slightly higher, of the order of 110 degrees. Another slide for the reactor vessels. The aging mechanisms have been already detailed this morning. We have spoken about thermal aging. The nozzles are the big pipes connecting the vessels and the steam generators. Now, it has also been touched upon by Commissioner Jamet. Our prognosis, our request, if you prefer, is an extended capability of operation of 60 years. Again, this is a request. We have good quality of design and manufacturing. We do detailed controls from the very beginning. We have good operations feedback. And for the 900 megawatt units, the regulator's first generic position beyond 40 years is expected in 2015. So again, this is a request. We are waiting for the regulator's answer. For long-term operation strategy, we used prognosis with deterministic and conservative approaches. So indeed, there is conservatism in the reactor vessels aging regulations. We use, of course, state-of-the-art methodologies to determine the stresses in case of transients. And we do mitigation and special inspection or surveillance actions. Low leak core management, this is the neutronic flux, by the way, has been touched upon. And we have also capsules inside the vessels, which we take out and which we perform mechanical tests to see how the steel is aging. And if necessary, as an option, we can increase the safety injection temperature. We keep this as an option to be discussed during the dialogue between the operator and the regulator. We have also spoken about the containment, the reactor building. For 900 megawatt series, we use one technology, one single wall and one metallic liner. And for our 1300 megawatt series and N4 series, we used a double wall and no inside liner. We do detailed studies about the aging phenomena of the concrete. We of course do a periodic pressure test every 10 years at the design pressure, which is of the order of 5 bars. And for the double wall containment buildings, we have special technological solutions which are under development. Now on this slide we take a look at many other components which can be replaced. Of course on the secondary part of the plants, but not only. For instance, you see here a steam generator replacement, which is a boundary between primary circuit and secondary circuit. You can take a look at INC modernization, you can take a look at generator rotor innovation or starter replacement. You can take a look also at the replacement on our condensers for the tube bundles of the units and also for the cleaning systems. Now, the regulatory context is performed within the framework of the French 2006 law, Transparence et Sécurité Nucléaire. Of course, we use as general policy, well, my country uses as general policy, continuous improvement of nuclear state safety. We take into account the best scientific knowledge. If there is any conservatism in some regulation, it has to be studied. We take, of course, worldwide operations feedback, and we take into account safety improvements of new reactors. It has been already said, we do periodic safety review, PSR, every 10 years, visite décennale en français. There is no limited licensing lifetime, but there is an opinion by the French Nuclear Safety Authority, and the opinion is, or advice to the government, is given on a case-by-case basis analysis for each unit. And the advice is for operation of an extended period of 10 years. Again, there was a generic approval for the 900 megawatt series, which was given in 2009. But once we have the generic approval, each unit is inspected, and the authorization to move on is given on case by case, unit by unit. Again, 900 megawatt series, 18 units have completed modifications, formal authorization given for 5 units. We have already implemented numerous modifications on our plants after the American TMI accident, after Chernobyl. We took into account for inundation the Blayais storm in the southwest of France in 1999, and we have also taken into account a heat wave in our country in 2003. Technical modifications are listed: sand filters and containment, hydrogen recombiners, new concept of emergency procedures, and the modification of the INC on the N4 series. Now, our safety goals for long-term operations, and this, as far as reasonably practicable, is a new word in European regulatory text. So for design basis accidents, we want to mitigate their consequences, and we want to avoid radioactive releases that would require off-site emergency measures, such as iodine ingestion and evacuation. We want also, as a safety objective, to continue to reduce the risk of core melt, which is already divided by 10 since the commissioning of the plants, in case we have any internal event. And of course, we want to significantly enhance plant resistance to hazards. And last very important safety goal is to minimize time and space related countermeasures in the event of a severe accident, making use of the important modifications which have been requested by our regulator as part of our post-Fukushima action plan. I recall the opinion of our regulators. Monsieur Jamet spoke about it at the general peer review in 2012. The regulator considers that the plants show a level of safety sufficient that enables them not to ask the immediate shutdown of any plant, This was 2012 conclusion. But the regulator considers that it is necessary to increase in a time as short as possible and beyond the safety margins already in place, the robustness of the plants to cope with extreme situations. And of course, we submitted an EDF action plan, and this action plan, submitted in late 2011, was taken inside the global country action plan, and it was shown and reviewed at the European peer review exercise of 2012. Out of time, I will not detail all the steps. It has 3 steps. Step 1 being adding of mobile devices and some non-permanent modification. The time frame is short, 2012 to 2015. Step 2, there are already permanent hardened means, the first one, to cope with the situations of water and electricity losses, which are more severe than today. And I will spend some time of step 3, which will be deployed from 2019 onward, and which is also part of the fleet lifetime extension. We complete the hardened safety core. For the steam generator residual heat removal, we add a dedicated feed water pump, we add a dedicated steam generator tank, and we add an ultimate water supply. We also want to add on a primary circuit the ultimate primary injection point, severe accident qualified. We want to add a new heat exchanger for containment residual heat removal, and we take into account requirements much more severe for extreme earthquakes and for flood. Once we have completed these 3 steps of our post-Fukushima action plan, we think it would be possible to reach on the existing fleet in operation a safety level as close as reasonably practicable to the safety level of the Generation 3 reactors. It is, of course, for the regulator to speak, but we feel that this will be a requirement of the French safety regulator to extend the operating life of the plants beyond 40 years. We have ongoing discussions with our regulator. We have started in 2008. We received an important letter, which many of you know, in June 2013. We say on our side, the method is gone. The methodology which EDF is using is a good one, but the regulators was right to point out that there are many new things to add and important work to perform between now and 2019. And 2019 is the planned outage of the Tricastin 1 unit. This is a 900 megawatt series, and operations will be requested beyond 40 years. This will be the first unit. Ladies and gentlemen, Madame la Députée, thank you.